Hello and welcome to Lab 5, Magnetic Braking with Faraday. So some introduction before we begin. The purpose of this lab is to observe a magnet falling through a conductive tube of aluminum foil, model the magnet-tube interaction in GlowScript, and then compare that model with my observed data. Some concepts we use today are Faraday's law, the Biot-Savart law, Newton's laws of motion, Ohm's law, magnetic field, force, and flux. Some assumptions we made today were that a bar magnet acts as a magnetic dipole, air resistance is negligible, and the only forces acting on the magnet are gravity and magnetic force in the plus or minus y direction. So the main results of our lab is that my experimental time was about 1.27 seconds, and our computational time was 1.24 seconds. And this timed the amount of seconds it took for the magnet to fall through the length of the tube. So for the experiment, here's what we did. The system was aluminum foil and magnet, the surroundings is everything else, and the initial conditions is that the magnet has not been dropped into the tube yet, and that there's no magnetic force acting or any induced current. So the process of the experiment is to begin with assigning the north pole to the bar magnet using a magnetometer app, and then you're going to drop that magnet into the aluminum foil tube as shown in the image. And this tube has to be non-ferrous to avoid activating other external magnetic fields. So we couldn't have done this with a steel pole or anything with iron. And then we recorded how long it takes for the magnet to enter and exit. And you can see the trials on the right side. And then we repeated it 5 times and calculated the average. And we got around 1.27 seconds. And the magnet falls slower than in free space due to the upward magnetic force from the induced current acting against gravity going downwards. Here's our computational model. We did the specifications of the tube, then we created the bar magnet, then we calculated the magnetic field of the bar magnet, and then we calculated the magnetic flux. Here we did the simulation loop, the magnetic force, gravitational force. Here we did magnetic field and the B field of each ring in the tube. And then we did an F-net equation, which is just gravity and magnetic, and then we did velocity and position update formulas for the bar movement, for the bar magnet moving down, and then we got this code running, and this is the graph at the end, and the simulation said that the time in the tube was 1.24 seconds. So some questions for the computational model is that the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring, and that red and blue indicates current flowing in opposite directions. So which color corresponds to clockwise and which does counterclockwise? So we said above the red is counterclockwise and from below the blue is clockwise. So what happens to the dynamics of the system when you flip the magnet? So this is when the south end would be going in. So nothing physical would change. It would still be a slower fall than in free space. But the B field and the B induced would flip. They would just go opposite. And then how does the total time of the tube compare to our real world system? So it's pretty accurate. It's only off by 0.03. We can make this even more accurate by splitting the tube into more rings, repeat more trials, etc. So what did the shape of the velocity graph tell us about the forces acting on the bar magnet? So we see in the beginning, here gravity is more prominent than the magnetic force, so it's uneven. And then throughout the middle, it's very even. It's falling at a steady rate. And then towards the end again, gravity is bigger and makes the magnet completely fall off the tube. So some questions. What is the resistivity of the conductor? What if the resistivity of the conductor was reduced as close as possible to 0? How would this change the magnet falling? So the induced current would increase due to Ohm's law, and then this would cause the magnetic force to increase as well, and then the magnet would fall even slower since now there's a more powerful magnetic force pointing in the upward direction against gravity. And then what if holes or slots were cut into the tube? How would this affect the current? So induced current would decrease since the holes would disrupt the uniformity. The magnetic force would decrease because of this as well. And then the magnet would fall faster down the tube than if it was even. So some conclusions, possible sources of error. There are not many. This is a pretty accurate lab. But we had a couple assumptions such as the magnetic dipole is a bar magnet. We said no air resistance. Most error probably came from human error using the stopwatch. And then the main results of the lab is that this experiment was relatively accurate and error-free, since our results were very similar between experimental and computational. Bar magnets act as good dipoles. Aluminum foil produces close to no external magnetic field, which didn't interrupt in any way of our experiment. And that Faraday's law is important in daily life. Thanks for watching.